An infinite series will look like this. This is just how we write it on paper. That's an infinite series. The sum as k goes from 1 to infinity of a sub k. That represents an infinite series. A sub 1 plus a sub 2 plus a sub 3. That's this. Okay? That is the same thing as the limit as n goes to infinity of the sum as k goes from 1 to n of a sub k. Which is equal to the limit as n goes to infinity of s sub n. So the infinite sum of a series like this, as n goes to infinity, will be the same thing as the limit of these partial sums as n goes to infinity. Sum 1 will be the sum of the first term, just that. S sub 2 will be the sum of the first two, so that'll be an answer for that, an answer for the first three. And we look at the sum of the limit of these answers to find the sum of the infinite series. And then we just simply say this equals L, which is the limit. Any questions? All right, I want to again, you don't have to write this down. These PowerPoints are available to you. I'm not going to ask you to memorize this and repeat it on a test. I just want to read it and make sure we all understand it. Definition, limit of a sequence. I think we might have looked at this already on Friday, did we? On Wednesday last week. You remember? We looked at this one? Okay. Let's read it again and refresh our memory. This is about a sequence. This is not a series yet. I've been talking about a series back here. This is backing up sequence. If the terms of a sequence, a sub n, approach a unique number L as n increases, that is, if a sub n, this is a sequence, not a series, we're not adding yet. If a sub n can be made arbitrarily close to L, be made as close as we want by taking n sufficiently large, by taking as many n as large as we need, then we say the limit of a sub n as n goes to infinity, so the limit of our sequence approaches or equals L. That means a sub n approaches L. Exists. And the sequence converges to L. So whenever it equals a finite value, we use the word converge. It converges to that number. If the terms of the sequence do not approach a single number as n increases, so they don't head toward a single number. Remember we saw some that went different directions? Okay, if they don't go to a single number, then there is no limit and the sequence diverges. So there was I remember us looking at this now. There was an example where it approaches a single number, 0, as you move to the right. These points approach the x-axis, which is y equals 0. So this sequence approaches 0. Notice the denominator is getting infinitely large. The numerator is just oscillating between -1 and 1. Okay. Here's an example where it's just jumping back and forth, 1, -1, 1, -1. It never approaches a single value. This one diverges. This one converges. This one diverges. All right? This one is going out like that. I guess it's this way. Going out like that. I'm backwards because I'm looking at the screen this way. That diverges. That does not approach a single value. Again, these are sequences, these are not series. Here's another one. This one approaches a single value. As you put larger and larger numbers in for n here, this approaches 4. You can see them approaching 4. Remember, we define these over the integers. That's why we don't have lines connecting them. No decimals or fractions are used. There's just points, individual points, not connected. Okay. Here's the ball bounce problem that we just did. And here's the height of the ball. It starts out with the first toss, it goes up to 20 feet. The first bounce, it's up to that value, third, fourth, fifth. And as we go to infinity, we see that this approaches 0. Okay? Here's the square problem we just did. So here's the formula. S sub n, 1 over 2, 1 over 4, 1 over 8, 1 over 16, and so on. It's 1 over 2 to the nth power. That denominator is going to infinity, so the fraction goes to 0. All right, I was leading up to this. This is the big one here. This is what we just now finished talking about on the board. Here's our sequence. The sum of its terms, this is called a series. So here, when they're separated by commas, that's a sequence. When you put pluses in there and make it a sum, now it's called a series. In this case, if we're going to infinity, it's an infinite series. The sequence of partial sums, S sub n, associated with this series has the terms, and this is what we did on the board right here. If the sequence of partial sums has a limit L, pay attention to the terminology here. So if there is a limit, a finite value that this sequence of partial sums approaches, the infinite series converges to that limit. And this is what we write. Got that on the board. If the sequence of partial sums diverges, meaning it does not approach a single value L, then the series diverges. Now be careful here. Just because it diverges doesn't mean it has to go to infinity. It's possible for the sum to jump back and forth between 1 and -1 and never approach a single value. So that would be a case where it diverges, or if the sum goes off to infinity, that diverges. So it can diverge both ways. So, terminology. Do we all understand the difference between a sequence and a series? We got that? And do we understand the difference between converges and diverges? Okay? We need that terminology in our head. Oh, that one. Okay, I got another example we're going to do. Time is Now this ball, in reality, does the ball bounce an infinite number of times? No. If it did, it would finish it in a finite amount of time, because the gaps of time are approaching 0 in between the bounces. But it doesn't bounce an infinite number of times because there's friction. Every time that ball bounces, every time it compresses when it hits the ground, atoms and molecules are rubbing against each other inside and creating friction. And they create heat. So energy is lost. Does that make sense? And you even have air resistance going on here. And that bleeds off energy. So this is a theoretical model if there was no energy loss. No friction, no air resistance, none of that stuff. And this is just theoretical. The theoretical usually is a good approximating model for a a small interval of values, but then when you get outside of that, it starts becoming further and further off. Does that make sense? So for a small number of finite values, 4 or 5 bounces, it's usually a good approximating model. But not when you get out to, it might not even get 1,000 bounces, so when you get further out there, then it falls apart. All right, here's a series. This series is 0.9 plus 0.09 plus 0.009 plus 0.0009 plus, I'm going to write dot, 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 meaning that continues indefinitely. So this is like, well, yeah. This is like a sub 1, a sub 2, a sub 3, a sub 4. Okay? Those are the terms of the series. Now let's look at the partial sums. S sub 1 is a sub 1, 0.9. S sub 2 is the sum of the first two, 0.9 plus 0.09, which is 0.99. S sub 3, sum of the first three terms, .999. Let's do another one. S sub 4 would be 0.9 plus 0.09 plus 0.009 plus 0.0009, which would be 0.9999. All right, do you see what's happening here? See the pattern? Let me get my thoughts together here for a second. All right. Notice that, I'll do this in blue, this is 9 times 0.1. Try that one. Notice that this is 9 times 0.1 plus 9 times 0.01. This is 9 times 0.1 plus 9 times 0.01 plus 9 times 0.001. One more. 9 times 0.1 plus 9 times 0.01, 9 times 0.001 plus 9 times 0.0001. Let's see.